This is our last section for linear regressions. So going back to this study about the 27 sets of identical twins, one twin was raised by the biological parents and the other twin was raised by foster parents. So in order to conduct inference on linear regression, we need to make some assumptions. We need to assume or to know that the true relationship is linear. So is the scatter plot roughly linear, and does the residual plot show any patterns? We're looking for linearity in the scatter plot and randomness in the residual plot. We should not see any patterns in the residual plot. We need our observations to be independent. If we're sampling without replacement, we need to meet the 10% condition. Residuals need to be normally distributed. So do a dot plot or a histogram of the residuals and see no strong skew or outliers. We need the standard deviation about the line to be the same everywhere. So the equal standard deviation. So we're looking for, does the scatter plot, are all the residuals on average about the same, have the same variability, or does the scatter plot show that the residuals get larger as X gets larger? Remember, that's called heteroscedasticity. And the residual plot may show this more clearly. We are looking for that fan-shaped or Christmas tree-shaped pattern in the residuals. That would be bad. That is not equal standard deviation. What we want is, again, randomness in the residual pattern, in the residual plot, so that everywhere has the same variability. And is it a random sample, simple random sample, or if it's an experiment, are the observations, the experimental units, whatever those may be, randomly assigned to treatment and control group. So, assume these 27 sets of twins comprise a representative sample of all twins separated at birth, and we want to test if these data provide convincing evidence that the IQ of the biological twin is a significant predictor of the IQ of the foster twin. What are the appropriate hypotheses? So our hypotheses are always about the parameter, not about the statistic. So B is the statistic. That's the sample slope. We know what B is. We don't need to conduct inference on B. We're making a prediction about the population slope, the slope for the relationship between the IQ of the biological twin and the IQ of the foster twin for all sets of twins separated at birth. And so the correct answer would be D. Beta 1 equals 0 and beta 1 does not equal 0. We've been using alpha and beta instead of beta 0 and beta 1. Beta 0 and beta 1 and beta 2 and beta 3, etc. Would be more likely used for multiple regression. But in this case, it would be beta 1 is the slope. So our null is that the slope is 0, there's no relationship, and our alternative is that the slope is not 0, there is some relationship. Here was the printout with the intercept and the slope. We don't typically do inference on the intercept because we've talked about how the intercept on its own is not really a useful point. it is often an extrapolation and doesn't have really a connection to any kind of real world application, right? In this case, that would be if the biological twins' IQ was 0, what would we predict the foster twins' IQ to be? And nobody has an IQ of 0. You would be actually literally dead. So that would not be, that's not a useful, it's not a useful term. It's not something that we would ever really want to do regression on. But we do want to do regression on the slope because we want to see whether we can conclude with statistical significance if there's a relationship between these two things. For regression, we always use a t-test. And the computer or your calculator will helpfully give you the standard error on the slope. And so you can find the t-test statistic. It's the point estimate minus the null value over the standard error. So your point estimate is here. So in this case, that'd be 0.9014 minus your null value. For a linear regression, our null is going to be 0, that there's no relationship. And then divide by the standard error here, which is 0.0963. And if you do that, you should get this, 9.36. So that's going to give you a t-value 9.36. And then if you didn't have this printout in your calculator, you would do the CDF with a lower bound of 9.36, an upper bound of 1E99. There were 27 sets of twins. Degrees of freedom is n minus 2. So 25 degrees of freedom. And our hypotheses were two-tailed, so we would multiply this by 2 and get the p-value. And it's going to be very small, less than 0.00005, whatever. Rounds to 0 at 4 decimal places. If you do it on your calculator, you could get a more precise answer. Note that this is always going to give you the two-tailed p-value. So if you need the one-tailed p-value and you're relying on this, you would need to divide that by 2. So our point estimate is the observed slope here. The standard error associated with the slope is the 0.0963. And so degrees of freedom is n minus 2. N is the sample size. We had 27 sets of twins. You don't need to worry about that. Alright, so our t is 9.36. Degrees of freedom is 25. And our p-value is going to be less than 0.01. It's very, very small. So statistically significant at the alpha equals 0.05. So if we were to do a false hypothesis test, we would need to state the hypotheses, the statistic, the parameter, and the alpha level. We would need to name our test. This is a one-sample t-test for slope. List our conditions, which were on the previous slide. Linearity, independence, normal residuals, equal standard deviation, and randomness. And then calculate the t-value and the p-value and make our conclusion. In this case, we would reject the null value because our p is less than alpha of 0.05, and we would conclude that there is a linear relationship between the IQ of the biological twin and the foster twin separated at birth. All right. So what can we say about the relationship between the percent college graduate and percent Hispanic in this sample of 100 zip codes areas in LA? It's a little bit difficult to tell looking at this, but like we can see, like the dark areas here on the college graduate map tend to be lighter over here, and the darker areas here tend to be lighter. This is darker here and lighter over here. We've got the dark parts in here have lighter parts here. So there appears to be a negative relationship, right? The areas that have the high college graduation rates here and here have lower percent Hispanic, and vice versa. The higher percent Hispanic areas tend to have lower college graduation rates. So there appears to be a negative relationship. Much easier to see looking at the scatter plot though, right? Here we can say that there is a strong negative linear relationship with one possible outlier, two possible outliers. Say that's probably an outlier and that's probably an outlier. That I want to know about. It says 0% Hispanic, but also 0% college graduation, which seems really, seems very odd. I don't know. I guess there are some other points that also have 0% college graduation, but this, I would want to take a look at the data and see what's going on there. So, a couple of possible outliers. But, yeah. So this is the regression output. So if we wanted to conduct a hypothesis test to determine if there's a statistically significant relationship between the percent Hispanic and the percent college graduates in these zip codes, then we would need to state, right, our parameter is that is beta, which is the true slope of the LSRL for percent Hispanic and percent college graduates for all zip codes in LA. Our null is going to be that beta equals 0. Our alternative, we could say that beta does not equal 0 or that beta is less than 0 because we observed a negative relationship. So it would be reasonable for us to test whether that negative relationship exists. And then an alpha equals 0.05. Our conditions are going to be, again, so name the test. It's a one sample t-test for slope. Our conditions are that it is linear, independent, which would be the 10% condition, normal residuals equal standard deviation, and random. And we would calculate, we would do our t-test statistic. Our general formula is that the test statistic equals the statistic minus the null value over the standard error. So that would be negative 0.7527 minus 0 over 0.0501. And that's going to give us a t-value of negative 15.01 and a two-tailed p-value of approximately 0. If we were doing this as a one-tailed test, we would double this, but turns out that when you double 0, it's still 0. Or sorry, halve this. We should divide this by 2. But when you divide 0 by 2, you still get 0. So, and then so our conclusion would be that we reject the null, and we do have convincing evidence of a negative linear relationship between the percent Hispanic and percent college graduates for all zip codes in LA. Right? If these zip codes are not randomly selected, remember randomness is one of our conditions. If they're not randomly selected, then we are not able to generalize to all zip codes in LA. It may be that we happened by chance to pick zip codes that show this negative relationship. Or not by chance, if we didn't do it randomly. We may have, maybe deliberately cherry-pick some data to make our point. For the confidence interval, right? A confidence interval is the point estimate plus or minus the margin of error. Again, the degrees of freedom are n minus 2. So which is the correct 95% confidence interval for the slope? This is based on the observation of 27 twins. So your estimate, right? This is your point estimate. Point estimate, your margin of error is equal to your t-score times your standard error. You are going to need to get that t-value using the inverse t. If we want a 95% confidence, right, that means 2.5% in each tail. So that's going to be 0.025. And 27 sets of twins means 25 degrees of freedom. So you would have to do the inverse t to get your t value for your margin of error. I am pretty sure it's this one. It should be, right, we need the one with the slope 0.9014 and the standard error 0.0963, and this is the z-score, so I think that is the t. Yes. And so that gives you a confidence interval of 0.07 to 1.1. So, just like with previous confidence intervals, we need to state our parameter, and so parameter, again, our parameter is beta, which is the true slope of the LSRL for biological, twin, IQ, and foster twin, IQ for all twins separated at birth. And then also our confidence level is going to be 95%. Plan, just like with the hypothesis test, it's a one sample t interval for slope, we have the same 5 conditions: linearity, independence, which in this case is the 10% condition, normal, residuals, equal standard deviations, and random. And so we have previously checked these conditions for this set. But we would need to, if you were doing a full confidence interval procedure for this on the AP test, you would need to explicitly check these things or state that they must be assumed. The do, your general formula is the point estimate plus or minus the margin of error. And then the work for that is here, and that gets you this confidence interval. And then we would state our conclusion. We are 95% confident that the interval from 0.7 to 1.1 captures the true slope of the LSRL for biological twin and foster twin IQ for all twins separated at birth. So, for a hypothesis test, your T statistic is the point estimate B minus the null value over the standard error with 2 degrees of freedom. For a confidence interval, it's B plus or minus T times the standard error. The null value is often 0 since we're usually checking for any relationship between the explanatory and response variable. Either there is a relationship or there's not a relationship. So our null is usually going to be that there is no relationship, that the slope is 0. The regression output gives you B, the standard error for B, and the two-tailed p-value for the t-test. If you need the one-tailed p-value, you divide by 2. You can also do it on your calculator. The calculator notes on Teams give you how to use your calculator to get the regression information. We are not going to do inference on the intercept. There's really no point to it. And always be aware of the type of data you're working with. For instance, a random sample versus a non-random sample, or is it a population? If it's a population, you don't need to do inference. There's no point in doing a confidence interval if you have data from the entire population. If your population is, say, 10 people, there would be no point in doing inference on that. And the randomness, if you have non-random data, then you are susceptible to different types of bias. We've talked about different types of bias that come from non-random sampling. So, yeah, statistical inference doesn't matter when you have the population data. There's no point. You already know everything that there is to know. If you have a sample that is non-random, then it is susceptible to different types of bias. And the ultimate goal is to have independent observations. When we're sampling without replacement, we will not get true independence, but if it's less than 10%, we say close enough. And that's it. This is the last section. Now it's time to study for the AP test. Hope you're ready.